Artificial intelligence has become the most important new methodology in scientific research since the adoption of quantum mechanics. Photonics is an ideal platform for artificial intelligence, as Maxwell's equations can generate reliable sources of training data for deep learning algorithms. While photonic systems offer a unique platform for implementation of artificial intelligence due to the parallelism and quantum nature of photonic technologies. We have a thriving collaboration between Nanyang Technological University in Singapore and Southampton University in the United Kingdom on developing groundbreaking artificial intelligence-enabled optical imaging and metrology technologies that can reach resolution down to the molecular level.
There are several ways in which AI can be a potent enabler for research into light-matter interactions. New forms of electromagnetic waves are still being discovered. Recent examples including singular beams and non-separable electromagnetic pulses. AI provides the tools to speed up our discovery of new electromagnetic field configurations, including those that are too complex to analyze using conventional techniques. AI can also be used to solve the so-called inverse design problem of how to design the photonic nanostructures necessary to generate these interesting electromagnetic field configurations. This has the potential to lead to advances ranging from wireless communications to spectroscopy and imaging.
Biological intelligence is usually associated with the connectivity of neural cells in the brain. Photonics offers brain-like platforms for neural networks that may help overcoming the bottlenecks of digital electronic processors. For instance, neuromorphic photonic materials with large optical nonlinearities can mimic synaptic plasticity. Artificially structured metamaterials can perform mathematical functions on optical beams nearly instantaneously. And photonic networks, made of optical fibers or planar waveguides, can reproduce the complex connectivity of biological systems. The development of new photonic materials and architectures for AI will open up new practical implementations where performing mathematical operations using light could be much faster and more energy efficient at specific computational tasks.
Laser machining is a highly flexible and precise manufacturing process. However, it is highly nonlinear and hence extremely challenging to model when starting from a theoretical understanding. Recent results have shown that neural networks can model laser machining with a precision almost indistinguishable from reality and taking just a few milliseconds per simulation. So far, we have used deep learning for modeling micro-scale femtosecond laser machining of metals. Analysis shows that neural networks can accurately simulate physical effects such as the diffraction limit, the production of debris, and the melting and cooling of the target metal. Deep learning will enable self-optimizing and self-correcting laser-based fabrication tools, capable of manufacturing the next generation of deep learning photonics hardware.
We have these really difficult problems in photonics, like reconstructing the object from diffractograms, that conventional mathematics struggles with. But artificial intelligence performs surprisingly well. And if you look inside a neural network, it's actually a black box. It's not clear how it works. And for us, for quite a few years, the task has been not just applying them to photonics, but also finding out how they work. And we recently made some progress and we found amazing things. We found neural networks inventing some of the modern mathematics, like digital filters, Chebyshev polynomials, things like that, all on their own, without human intervention. And so far, we are seeing them invent the mathematics that humans already know about. But potentially in the future, they might invent something new. And so these neural networks, in principle, could be mined for new knowledge.
AI has achieved tremendous success over the last few years, and it can be certainly applied to both the research in photonics to make better predictions and decisions. There are several research directions where AI can be used to help photonics research. leveraging the universal approximation ability of neural networks to learn the unclear relationships between different variables and sources. Applying deep learning techniques to automatically find nodes from the experimental data, where nodes are represented by human understandable notations, and integrating domain knowledge into neural network-based approaches to improve prediction accuracy and decision efficiency.
We are passionate about wide adoption of artificial intelligence in the science of light, as it can be adopted to developing advanced functional photonic materials, metamaterials, optical circuits, and nanophotonic devices, solving fundamental problems of light-matter interactions and optimizing optical telecommunication and light-assisted manufacturing technologies.